somewhere in Moscow or in Yaroslav. By the way, I never visited Yaroslav, and I see this as a sort of this idea that after the pandemic, then maybe we can indeed meet in person in your beautiful city. I spent many years, many nice years in Moscow, and visited Moscow on many other occasions. I visited Suzdal a few years ago, but Yaroslav somehow was still out of my reach. So I'm very glad to have a chance to share some of my interests and some of our results with you. Also Dmitry announced this as a potential part of some maybe a little bit longer course, and we still need to discuss details. So today I'll try to present some overview of an activity which actually occupied my interest for many years. And so in 2011 appeared our book, where we collected some results of previous more than 10 years, maybe 10-15 years. But then after that, we still continued to work in this field, and some of most recent results are presented in these two papers. But there are also several papers and results which span these periods from 2011 to 2019 and 20. So the book also has a Russian edition. Actually, it first appeared in Russian, published by Regular and Chaotic Dynamics in 2010. And the title is not exactly a literal translation of this English, but you can easily find, and there is an exact title in the announcement of this presentation. There are also a couple of papers published in I think in 2010, in 2015 in Uspekhi of in Russian marked surveys to connect with the Russian audience. So talking about modern from the modern perspective, so I would say this is like a Poncelet theorem and ramifications, and then within this almost now 25 years, we collected quite a lot of ramifications, and we are very glad about that. So this particular diagram I made a couple of years ago here in Dallas, the Department of Mathematical Sciences. We organized a sort of a fair where each professor got like 10 minutes to present their field, and then to hope to attract some graduate students. So since I had like 10 minutes, I decided to prepare this sort of diagram. I tried to explain in 9 minutes. And I had some student who was interested in working with me before that. And then after I gave this talk, not only that I didn't get any new students, I even lost that one. So still, I'm not giving up. I want to present this, and maybe this with this seminar in Integrable Systems organized in Yaroslav, I'll be more fortunate, and maybe some potential students would see this as something which is to see this as exciting as I see. So what we managed, so I put in the center is Poncelet theorem and integrable billiards, and this is the topic of our today's talk. But then nicely it connects with algebraic curves or Riemann surfaces and their Jacobians. This is this upper vertex. Then Penlevé equations and isommonodromy deformations, and also extreme polynomials, approximation theory, and potential theory. So you can, of course, organize this diagram as a tetrahedron, and then as a tetrahedron, due to its symmetry, you can rotate and play with this, and then you can put whatever vertex you want on the top. In a sense, you can declare any of these topics as a dominant, and then see others as branching starting from here. So I'm really very excited about this cross fertilization of fields and this cross pollination, as they say. And many of these fields and topics are quite classical, but in this interaction, we managed to get new results in each of them. So, and I in the title I put 4 areas and then arrow to 5 areas. The 5th area, which may appear today depending on time, is also combinatoric. So we also found very interesting new connections with, in a sense, new objects in combinatorics. So I was requested to have 15 minutes of very clear introduction. So let me execute this. So suppose we have 2 conics. Suppose we have 2 ellipses, one inside another. And then we play, let's say, a geometric game. We start from outer conic. And I think you see my this hand, huh? You see this? Yes, huh?
Yes, it's perfect.
Okay, very good. So you start from this one point, from outer ellipse. Then you have a chance to construct, because these are conics, you can construct 2 tangent lines to inner conic. So you select one, let's say the right one. Then, since this is then the outer curve is conic, you have a second intersection. Then you find the second intersection. Then from the second point, you already have one tangent you came from, and then there is only one new one. Again, the right one. You can go so you can go like this. Then you go the second move. You tangent and you get another point. You tangent the inner conic and intersect the outer conic. Then again, you repeat the procedure. You tangent the inner conic and intersect the outer conic. Then you tangent inner conic, intersect the outer conic. And then once again, you do the same. And then what happens here is in the next move, you again do the same. And then now, after, let's see, 1, 2, 3, 4, 5, 6, 7 moves, 7 steps, you're coming back to the initial point. It's not going to happen all the time. If you choose 2 other ellipses in similar position, it may not happen. But if this happens once, starting from this point, then if you start from any other point, let's say this blue one, this is some arbitrary point, but you keep these 2 ellipses fixed and play the same game. Now I'm going this blue tangent line, intersect the outer, tangent the inner ellipse, intersect the outer, and then repeat second time, third time, 4th time, 5th time, 6th time, and then tan. This is now the 7th, and again going back to the initial point. So you see that the Poncelet porism, the Poncelet theorem says exactly this. So if your 2 conics are organized like this, that if you start and play the above described game, starting from one point, and if it is periodic with period k, then starting from any other point, it's going to be periodic with the same period. Here, the period is 7. So it's a very non-trivial result, and by many seen as the most beautiful result in actually projective geometry, because this is a completely projective geometric state. So here is the theorem, and the year is probably quite known to everybody with Russian's heart. So it's 1813. So if there is a closed polygonal line inscribed in a conic and circumscribed about another one, then there are infinitely many such polygons. Moreover, all of them have equal number of sides. And here by polygon, I have in mind polygonal line. They can self-intersect. So here is an artistic view on that time. So this is a Battle of Krasnoy, Bitva Krasny. There was one of these final battles of army of Kutuzov and Napoleon after Napoleon's retreat from Moscow. Battle of Krasny by itself was a battle between troops of General Milorádovich and Marshal Ney. And in this battle, our main hero, at that time, captain of engineering armies of French army, Poncelet was captured by soldiers of General Milorádovich, and he got transported to as a prisoner of war to camp of prisoners of war in Saratov, and there he spent more than a year, and he amazingly was involved in refreshing his memory about the classes in projective geometry, which he had in École Polytechnique by Monge and others. So I think he didn't have much of books, but he had notebooks, and he wrote the things, and that was published many years later as Saratov Notebooks. Saratov Notebooks in French by Poncelet, and in this period of captivity, somehow he got inspired enough with this environment and produced this one of the nicest theorems of projective geometry. Of course, in 1814, the situation settled between two countries, and Poncelet returned back to his country. He had one of the most prominent careers, not only in science. He got important military positions, important state positions, also became academician and one of the most distinguished scientists and statesmen of his time. So here is the misprint, say 1913 should be 1813. So using analytic geometry, he proved a generalized statement, and I will say a little bit more about this. So this is the full Poncelet theorem. Then another important mathematician of that time, Jacobi, reproved the Poncelet theorem and showed that this equivalent to addition theorem for elliptic functions. Then one of the most prominent mathematicians of 20th century also was Lebesgue, known for his construction of measure and integral, some very abstract mathematical modern objects at that time, was also very much interested in this classical subject. And he has a beautiful, short but beautiful book or booklet. I think it could have been that it was published after his death, but about conics. And he gave a very nice synthetical proof of Poncelet theorem, also using algebraic geometry in a non-trivial way. And then there is from modern times, well-known specialists in algebraic geometry, major modern American mathematicians, Griffiths and Harris, published a nice sort of modern edition of this proof, which attracted the attention of modern mathematicians back to this subject. And I miss here one important moment. This is a Cayley's result from middle 19th century, around 1853, where he derived algebra geometric condition. So give me two conics, and then Cayley can give you algorithm to answer, is this process which I described going to be periodic with given period K or not? So this is Cayley's result from 1853, which should be in this list. So, but that was a purely, let's say, geometric game or projective geometric game. But now we can switch a little bit, just a little bit, our focus, and we can present this as a mechanical problem. Again, of course, mechanical problem. So we can consider, so what we had before, we assume in advance that we have two conics, and just for the sake of the presentation, we assume that they are one inside another, and then we explained this sort of game, but we didn't use anything except incidence. So point belongs to a conic, and tangency, and intersection of line and conic. But here we can organize this now as a sort of a mechanical problem. of course, with the big mathematical abstractions and simplifications. So we can consider a dynamical system where a particle of, let's say, unit mass, which is just a geometric point, is moving without friction inside the domain and reflecting absolutely elastically on the boundary, meaning that we impose this geometric rule of billiard reflection that incident and this reflecting angle are equal. So trajectories are then polygonal lines with vertices lying on the boundary with congruent impact and reflection angles at each vertex, while the particle speed remains constant. And then we consider a specific case where the boundary is not arbitrary one, but it's an ellipse. The boundary is an ellipse. And then in specific situation, this is the focal property of conics. If you start from one focal point, here presented here, and then if you hit in any direction, after reflection, it will come to another focal point. This is just a focal property one of the versions of very well known classical focal property of ellipses. But using this property, we can prove the following. So now our assumption is that the reflection of the boundary satisfies this geometric billiard law. This is the assumption. And then we can prove that in this case, there will exist a caustic confocal with a boundary with the property that every segment of a billiard trajectory or its continuation is tangent to this one and the same conic. So in this Poncelet type story at the beginning, we assume that we have two conics and we organize the game as I explained. Now we assume that we have a billiard reflection of the boundary, and as a consequence, we are getting this second conic caustic. So there are three regimes here. So there are three main regimes. One I explained on the previous slide. So if you start from a focal point, then after any reflection, you will come back to a focal point. So there is one regime when each time you're passing through a focal point. And this is very singular regime. So let's forget about this for a moment. Apart from that, there are two main regimes. And here they are presented in two colors, red regime and blue regime. So suppose that we have a red regime. So what is the red regime? The red regime is the situation where we have a initial billiard segment which does not intersect the line defined by focal points. So here there is a segment. There is a segment with focal points as endpoints. So this red segment does not intersect the segment defined by focal points. After reflection, you're getting a new red segment, and again it does not intersect this segment defined by focal points. And it will go on and on like that. In this red regime, the theorem, this is a theorem now, it's a consequence, we can prove that there exists a conic, this red dotted ellipse, confocal with a boundary, with the property that each segment of this trajectory is tangent to this dotted red ellipse. So this trajectory is not necessarily periodic. It may have infinitely many segments. Each segment is tangent to one and the same, this red dotted ellipse. So this is one regime. This is this red regime. And there is also blue regime. In the blue regime, our initial segment, this blue one, intersects the segment defined by focal points. And after reflection, we are again getting blue regime, a blue segment, which is in blue regime, meaning that again it intersects the segment defined by this focal point. In this case, it's a theorem. There exists a confocal conic, this time this dotted blue hyperbola, confocal with the boundary with the property that every segment or its continuation is tangent to this hyperbola. These caustics, the existence of caustics this way or another, it may be hyperbola, it can be ellipse, is geometric manifestation of integrability of this problem.
Vladimir, I plan to talk a little bit more about the definition of integrability in this case. What does it?
No, not today.
Okay.
Not today. So I will say that there is some quantity which is preserved. So what is preserved here? This is this caustic. This is something which is one and the same for all segments of a given trajectory.
But is there some Poisson interpretation?
Yes, we can rewrite this in this form. Yes, we can rewrite, and we can also find, we can define the function. We can write it explicitly, a function which is going to be the first integral.
Okay, thank you.
But we're not going to play with this today.
Ваше интернет-соединение неустойчиво.
So now we are again in this iteration of Poncelet theorem, but now from the point of view of billiards. So now we assume, so what is the difference? So now we assume our basic assumption is that the reflection is a billiard reflection. And then we are getting this caustic as a consequence of that. In the original Poncelet theorem, we just had two conics. We didn't have anything about any reflection law. We just said whatever happens, happens. But now we have this caustic as a consequence, and now we can apply Poncelet theorem, which would then tell us in this particular instance that then if we started with one trajectory, let's say this red one, which had this dotted ellipse as a caustic, and if it was periodic with period k, in this case it was periodic with period 3, then any other trajectory, billiard trajectory with the same caustic, would have the same period. So this is now application of Poncelet theorem in this billiard setting. But now let me tell you something about great Poncelet theorem in this setting. So now the great Poncelet theorem is a generalization. It was known to Poncelet himself that you may consider not only one conic from confocal family's boundary, but you can have few of them. So here we have this gray ellipse as a caustic, but now we have here three boundary ellipses. And then you see that, for example, if we start from here, from the smallest of these three, and then we reflect of the third, and then reflect of the second, then again of the second, then again of the second, and then come back to the first, we are getting some sort of a periodic or a closed polygonal line with 1, 2, 3, 4, 5 sides. But now these reflection points belong to different boundary conics. All of them belong to the same confocal family. Now, if we start from some other point, let's say now from this point, and now play the same game, we start from the first, then reflect of the third, then reflect of the second, then reflect of the second, then reflect of the second, and come back to first. We are again getting a polygonal line with 5 segments with the same order of reflection of different caustics, and which is again going to be periodic. So you see, this is sort of this Poncelet porism, but in a more general setting, because now we have possibility to have several conics as boundaries. I said something that here we preserve the order, and we can preserve order, we can even change the order. So if there is a theorem here, important projective geometric statement called double reflection theorem, which actually gives us a sort of a projective geometric configuration present here, which allows us to even switch the order. So we can even switch the order. So we made this sort of here, this change of this part, we changed with that part. So in that case, let me just see how, oh no, okay. So now we see that we can replace, if we have this solid red 5-side polygonal line, we can replace it with, and that was like, so what was here? It was here like a first conic, order of reflections was first conic, third conic, first conic. So sorry, it was first conic, third conic, second conic, second conic, second conic back to first conic. That was the solid red. We can then there exists also the following one. First, this is going to be a combination of solid and dotted. So this is from the first conic, third conic, second conic, second conic. Now we skip this. Now we reflect here. Sorry, now we reflect here of the first conic. Go back to second. Now we skip this one here from the first and go directly to the third. So moral of the story is that there is a projective geometry configuration which allows you to even change the order of caustics in this construction. Still, it's going to be periodic with the same period and with the same boundary conics. The order may vary. So there is some commutativity here. And here is one statement from a nice, very important treatise of Darboux. I'm not going to torture you with my French. So if you know French, please read, or if you don't know, read again. I'll give you 3 seconds for me to take just some water. So Darboux also was one of these major mathematicians who was occupied with this topic for about half of a century. So about half of a century. And he made a tremendous contribution. And one of them is this Darboux theorem, which I tried to explain in this figure. So it looks a little bit like this. It reminds me, there is this very nice cartoon of Donald Duck explaining billiards. And then he got completely confused. So somehow this figure may look like this, that we're all completely lost already. So what we have here is, so we have here, first of all, we have a caustic fixed. This is this inner ellipse. And everything what we're talking about are lines which are tangent to this fixed caustic. And now we have 2 polygonal lines, blue one and green one, which are they are billiard trajectories within this. Let's say I will call this like let's say boundary 1 and boundary 2. Sorry. Oh. So let's look at this. Let's try to unwind this in our minds. What we have here. So we have a blue one. The blue one reflects from the boundary 1 once, 2 times, 3 times, 4 times, 5 times, 6 times, and once from the boundary 2 and goes back. So this is a periodic billiard trajectory which bounces 6 times off the boundary 1 and once of boundary 2. The green has the same property. The green has the same property. This is a periodic billiard trajectory which bounces 6 times off this boundary and once off the boundary 2. Now, I want to explain one instance of Darboux's theorem. which is now let me just try to see what I want to say. So let's call this segment starting from boundary 2 on the left. Let me call this the first segment. Let me call this the first segment. So if this is the first segment, then let me count. This is first segment, second segment, third segment, fourth segment. So what I see here is that first segment of this green trajectory and fourth segment intersect on this red ellipse. So first and fourth intersect on this red ellipse. But now let me see further. What if I go further, and now if I consider the second segment of green, this is this one, then it's going to be third, fourth, fifth. So look, then second segment of the green trajectory and fifth segment intersect again in the same caustic, the same conic, this red ellipse. So first and fourth segment intersect here, second and fifth intersect here. So what about this point? This is first, second, so third. So this is third, and fourth, fifth, sixth. So here intersect third and sixth. So what we see here, this is the intersection of first and fourth. This one is intersection of second and fifth. This one is intersection of third and sixth. So you see, there is the same shift. I go first, 1 plus 3, 4. First and fourth, they intersect on this red ellipse. Second, 2 plus 3, 5. Second and fifth intersect on this red ellipse. Third and sixth intersect, and so on. And if I apply the same procedure on another similar trajectory, the blue one, again, the first segment of a blue, this is second, third, and fourth, they again intersect on the same blue, red ellipse. So in a sense, what we see here is that we are actually getting a net of confocal conics involved here, which are going to be intersection points of different, so we can say that billiard trajectory is, and the boundary is intersection of consecutive segments. So first and second, second and third, and so on. And this red one is intersection of segments with shift 3 here. So first and fourth, second and fifth, and so on. But changing this difference here, for this red one is 3, but you can take it 2, you can take it 5, and so on. You're getting a net of confocal conics with this configuration property. So this is the Darboux theorem. So interestingly enough, we managed to generalize this classical result more than a century later. And we generalized in 2 steps. And here I'm going to explain only the basic step. We generalize this in the plane, and later on, I mean, I can talk maybe next time about the generalization of this in any dimension. But what is generalization here in the plane? So generalization here in the plane is that we don't need to consider first at all only periodic trajectories, as it was case for in Darboux theorem. We can consider any trajectory. Moreover, so caustic, we can consider caustics. We generate not necessarily periodic trajectories, but we can consider caustics, arbitrary caustics, and they may usually, in a sense, they generate non-periodic. And instead of looking, in a sense, self-intersection, like first segment and fourth segment of the same trajectory, we can take any 2 trajectories, here blue and red ones, with the same caustic, and then playing the same game. We look at the intersection of the first segment of the first trajectory and the first segment of the second trajectory. Then second segment of the first trajectory and second segment of the second trajectory. Third segment of the first trajectory, third segment of the second trajectory, and so on. And again, we are getting these confocal conics. Here, this is an ellipse, which contains all intersections of pairs of segments in this order, as I said. Here we have 4 possible situations, which correspond to 4 possibilities. We have 2 possible caustics. They can be ellipses. This is this front, this upper layer, and it can be hyperbola. This is this lower layer. And we can wind both. So since we are considering 2 trajectories, we can wind them both in the same direction. This is this left side, or we can wind them in opposite directions, and this is we get this right side. So altogether, we have 4 situations. Caustics is ellipse or caustics is hyperbola. We are winding in the same direction. We are winding in opposite direction. So there is here is ellipse, the same direction. Here is ellipse, opposite directions. Here is hyperbola, same directions, and here is hyperbola, opposite direction. So big part of our study is not in the plane, but in higher dimensions, in arbitrary dimension, starting from 3. And what is a challenge starting from dimension 3 up is the big difference, big naive difference, but still difference, is that in the plane, in the projective plane, any 2 lines intersect. And starting from 3 dimensions, most of the lines don't intersect. So, and here in this Darboux theorem, it's very important that these lines intersect, because we consider intersection of the first segment of the first and the first segment of the second, and so on. Even if you consider the same trajectory in the space, it's not clear that first segment and third segment or first segment and fourth segment need to intersect at all. They don't need to intersect. So then the big question is, how could we generalize Darboux theorem in space and arbitrary dimension? And we managed to do this. So I may talk about this in some of these next talks. So one important dynamical characteristic, of course, is a rotational number. So here you have few cases. We are talking about these 7 periodic trajectories, and then depending on how many times it goes around the origin during this one period, you may have these 3 natural different situations. So in the first time, you have ellipse as a caustic, and it goes around. You're getting this convex 7-gon, heptagon. Here it goes 2 times around, and you're getting something which is like 7-star, what is it, 7-point star. And here you also have getting some 7-point star, but it goes now 3 times around this caustic. And of course, you have different caustics in these situations. And here is natural to say that rotational number is 1/7. Here is rotational number is 2/7, and here rotational number is 3/7. And you can see that the rotation number changes monotonously from 0 to 1/2 in the case of ellipses as caustics. But you can also have hyperbola. We can also have hyperbola as caustic, and then this situation is not that easy. Actually, monotonicity in this case is very difficult to prove, and is not even obvious. And you can look at this Dustermite book from 2010, and you can see one very involved proof using elliptic surfaces. So there is yet another proof in this paper in 2019 from Communication Mathematical Physics, which I quoted at the beginning. Now, let me make a small historic break. There is one interesting, in a sense, historic coincidence. I already mentioned Poncelet as obviously one of the main authors in this area. But there is also interesting connection with the famous Russian mathematician, father of St. Petersburg School of Mathematics, Chebyshev. So, so there is this interest of Chebyshev in approximation theorem, which came from, at that time, so that was dictated by technology. So there was this Watt's complete parallelogram, which was this mechanism to transform linear motion into circular. And then the question was about errors. And that was something which occupied attention of Chebyshev. But Poncelet was also interested in that. And Poncelet, along this line, started to consider the question of rational linear approximation of square root of 1 plus x squared. And then somewhere around this Cayley's, when this Cayley's result appeared, just after this mid of 19th century, Chebyshev traveled abroad. And there is a very nice report, like Associate Professor Chebyshev, report on Associate Professor Chebyshev trip abroad. And so, you know, in this classical times, people, actually we also write these sort of reports, even nowadays. But I know my personal feeling when I write these reports is always, oh, one more report and why I'm doing this and somehow, and then put some, who knows something, but, you know, people who know what they're doing. So Chebyshev made a nice report, and this report we have, it's important. And then it's interesting that, so he knew about Poncelet results in this, talking about, about the specific question of approximation. And he described Poncelet as well-known scientist in practical mechanics. So not as a most distinguished geometer of his time, but as a well-known scientist in practical mechanics. So now we are switching the page. We are going to something which is the main field of our study.
Excuse me, could you for a moment switch to previous pages?
Sure.
A few pages. It's about the intersection of different trajectories.
Sure. Here or previous?
Yes, here. So the confocal ellipse of the intersection points of two trajectories, how it is described in terms of the elliptic curve. So
can you say once again?
I suppose that it is also an integral. So the parameter of this ellipse in the confocal family, could it be explained in terms of the underlying elliptic curve?
So in order to get elliptic curve, we need information about two things. We need information about, one way to see it, which is relevant to your question here. We need to have information about confocal family. This is, so for example, we give confocal family in this form, let's say x squared divided by a minus lambda plus y squared divided by b minus lambda equal 1. Then this a and b are parameters of this confocal family. And then we need one more parameter, one more piece of information. This is specific lambda for which this, which describes this caustic. So let's call this lambda. So this is an element of our confocal family, this caustic. So its value lambda is some lambda 0, let's say. Then elliptic curve, which underlies these dynamics, is y squared equal x minus a times x minus b times x minus lambda 0. Okay. So what I want to say is, once you fix confocal family, once you fix caustic, then elliptic curve is fixed. It means that, and then billiard dynamics induced by different boundaries from the same confocal family corresponds to different elements for different points on this elliptic curve.
Absolutely. But how the green point is related to the first 2 points corresponding to 2 trajectories?
Yeah. But there are no 2 points here because these two trajectories are obtained by reflection of the same boundary conic. So in a sense, they have the same point of elliptic curve corresponds for their dynamics.
Okay. Okay.
And this one would gain a different element.
Could you repeat?
This is like okay.
Okay. Excuse me.
No. It's excellent question. It's excellent question. But I'm just saying that it's not. We need to understand that not every single trajectory has its element in this representation, but the whole class of trajectories generated by the same boundary.
Mm-hmm.
This is a good question. Maybe we can explain this in one of the next talks.
Okay.
Yeah.
Thank
you. Good. Okay. So what I want to say now, I'm switching again. I'm switching a little bit. Let's say in the next 10 minutes or so, I just want to say something a little bit more about that. We want to talk about that the main focus of our interest is actually higher dimensional cases. Although you see here and there, the mathematics is so fascinating that if you work hard, you can even find some new results in something which is very, very classical. But here, I just want to say, elementary differential geometry can tell you, or just common sense can tell you, that you can consider this sort of billiard motion not only in the plane, but let's say in the space, let's say in 3-dimensional space. You can assume that you have a boundary, which is an ellipsoid, let's say. And then you can assume that you are sitting inside and playing billiard within this ellipsoid shell. And then, again, you assume the trajectories are straight lines, and then there are reflections of the boundary, and you can define them properly because you have, as soon as you have metric and everything, you can easily define what deflection is and everything is well defined. And then questions which we were studied recently were about what would be the shortest periods of periodic trajectories in dimension D. So we fix dimension D, and now we ask what is the shortest period of periodic trajectory. And then we need to make one here nuance. We need to say what is the shortest of essential trajectories. So we need to introduce here notion of essential and non-essential. So if you're going to higher dimensions, we will say the trajectory is a non-essential. If you're talking about dimension D, we will say that the trajectory is non-essential if it is completely placed in some subspace of lower dimension. So if the whole trajectory is contained in D-1 dimensional space or less, we will say that it is non-essential. It's non-essential because then we can study it by means of the space of lower dimension. So our question is, what would be the shortest period in a dimension D of essential periodic trajectory? So this is the question. So I think the question is clear, and the answer was quite challenging. So apparently it's D+1, but why is it so? And now let me come back let me go back to, I'll go back and forth between high dimensions and low dimensions. Let me explain one more thing. So about billiards in the plane with an ellipse. So again, you saw this picture. We have these two regimes. There is this red regime when the caustic is ellipse, and there is a blue regime when caustic is hyperbola. And then in this blue regime, you see in this blue regime, every segment intersects this segment defined by endpoints with foci as endpoints. So that means if you have a periodic trajectory in this blue regime, if you have a periodic trajectory in the blue regime, it means that the period has to be even. Because periodic trajectory means that you, after a period, you're coming back to initial point. Since each time you intersect x-axis and you come back to initial point, it means that you intersect x-axis even number of times. So from just this simple observation, we prove a theorem. We prove a theorem that if you have a three-periodic trajectory, then its caustic is always an ellipse. It cannot be hyperbola. Moreover, if you have odd periodic trajectory, its caustic is always an ellipse. It cannot be hyperbola. And these two periodic trajectory, these are those non-essential here because you have two periodic trajectories along y-axis and along x-axis. These are two periodic trajectories. They are placed completely in a subspace of lower dimension in an axis. So it's a dimension 1 here in two-dimensional space. So two periodic trajectories are trivial, are non-essential. And three periodic trajectories are going to be the essential trajectories with the smallest period in the plane. And here we conclude from this simple parity argument that their caustic cannot be hyperbola, it has to be ellipse. So now we are going to higher dimensions. And of course, unfortunately or fortunately, we don't have such a nice description of confocal families in higher dimensions as we have in the plane, that you have two focal points and then all conics with the same focal points form a confocal family. There is no such a nice description of confocal family of quadrics in an arbitrary dimension, but we can use this analytic expression and we can say that we are in d-dimensional space. We consider with fixed lambda, we consider all x1 to xd such that this relation x1 squared divided by a1 minus lambda plus xd divided by ad minus lambda equal 1, where we give in advance positive distinct parameters a1 to ad. So for different lambda, we are getting a family of confocal quadrics. And then we can fix a point now. We can fix a point, suppose this point here, which is in this picture in the intersection of these three quadrics, one ellipsoid, one sheeted hyperboloid, and one two-sheeted hyperboloid. So I fix this x1, x2, x3, and then I can ask the question for this fixed x1, x2, x3, for this fixed point, what are all possible lambdas which would satisfy this equation? So in the case of d equal 3, it's going to be cubic equation in lambda. In this cubic equation in lambda will give me lambda 1, lambda 2, lambda 3, which are going to be parameters describing ellipsoid, one-sheeted hyperboloid, and two-sheeted hyperboloid. For given this x1, x2, x3, obtained lambda 1, lambda 2, lambda 3 in this space are called Jacobi coordinates, Jacobi elliptic coordinates. And Jacobi introduced these coordinates in his lectures in dynamics, in 26th lecture in his lectures in dynamics. And then he solved the most important unsolved integrable problem of that time, geodesics on ellipsoid using elliptic coordinates. So these are the coordinates. And but before doing that, before solving the problem he wanted to solve, Jacobi solved a simpler problem, a little bit simpler problem. So this is integration of a straight line in d-dimensional space in elliptic coordinates, and he got these beautiful equations. But you see that this is actually equation written in form of differentials on hyperelliptic curve, and here we are getting underlying hyperelliptic curve y squared equal a1 minus lambda dot ad minus lambda, then alpha 1 minus lambda dot alpha d minus 1 minus lambda, where a1 to ad are parameters of this confocal family, these distinct positive numbers, and alpha 1 to alpha d minus 1 are parameters of describing caustics. So in higher dimensions, so in the plane we had one caustic. in three-dimensional space, we will have two caustics. Two confocal quadrics are going to be caustics to each billiard trajectory, each segment of billiard trajectory within ellipsoid in three-dimensional space. In d-dimensional space, we will have d-1 caustics. So you see that with dimension, the number of caustics increases. That corresponds to the fact that number of first integral increases, and all these systems are integrable systems. So the existence of these caustics in given number is again geometric manifestation of integrability of these systems in this case. And now we need to study how these elliptic coordinates behave, how they behave along one period. And for this, I have another presentation for you. So I will try to show you this presentation. So this is some small technological challenge for me. I hope it will work. So I request your patience a little bit. So now what we are going to do, I try to show you some experiment. So now, look, what you see is, you see situation in the plane, you have billiard trajectory with ellipse as a caustic, and then 0 here, you have two segments. One segment is segment where lambda-1 coordinate, Jacobi coordinate changes, and the second segment is where lambda-2 coordinate changes. And you see how they simultaneously change when you go along trajectory. So the endpoints of the segment 0 correspond to reflection of the boundary. Alpha, this is the second endpoint of the first segment, correspond to touching of the caustic. And then B and alpha, the first and the second endpoint of the second segment, correspond to the crossing to the x-axis and y-axis. So enjoy, look how it goes. So now we are coming to intersecting. We are now going off the caustic, off the boundary. We pass it through 0. Now we are touching the the caustic. We are going back, and here, look. So we are coming to this. Okay, this is with ellipse as a caustic. Do I need to repeat this?
Yes, it is very beautiful.
Should I repeat?
You could. So it's a linear move in this course.
No, it's not linear. It's not linear, but it is monotonous. It goes monotonously. You see what happens? It goes monotonously. They go from the lambda-1 goes from 0 to alpha, then from alpha to 0. Lambda-2 goes from B to A, then from A to B. There is no points, some midpoint where it may change its mind. Now go a little bit back, but go a little bit up. No, it goes monotonously from one endpoint to another. And now the question is, the big question is there any correlation between these two movements? So, or lambda-1 and lambda-2 completely independently somehow move.
Can we see it one more time, please?
Yeah, I'll show one more time. Yes, okay. Let me try. Sorry, I hit the wrong button. So now we touch the caustic. we are hitting this alpha on the left-hand side. Now we are touching the boundary. We are hitting 0 on the left-hand side. Now we are passing through x-axis. We are hitting B on the right-hand side. Now we are passing through y-axis. We're hitting A on the right-hand side. And I have also similar presentation for hyperbola. Now, on the left-hand side, we have 0, which corresponds to the reflection of boundary, and B, which corresponds to passage to one of the coordinate axes, and alpha, which is caustic here, hyperbola, now is left-hand point of the second interval. So now we are hitting B on the left-hand side. That means that we are passing through x-axis. We are hitting alpha, which means that we are now hitting hyperbola. Again, we are hitting hyperbola alpha, passing through x-axis is B. Now on the right-hand side, we are going to pass through, first we pass through 0 on the left-hand side, and now we pass through A on the right-hand side, which corresponds to passage through y-axis. Okay, so that was this moment of technology. Now let me go back to our presentation. So we saw what is going on. We have now some experimental some experience. What is going on in a two-dimensional case? In d-dimensional case, we will have d intervals. We will have d intervals, and then again endpoints would be 1 would be 0, which is corresponds to reflection of the boundary. Then it will be some alphas. Some endpoints would be alphas, which correspond to touching a caustic. This is the second bullet here, and there will be some a's, which correspond to some crossing coordinate hyperplane. Now the question is, what is the combination? There are several questions here. What are possible combinatorics? How these A's and alphas are organized? How these endpoints are organized? And the second is there any correlation between these dynamics of these lambdas? For example, you're going one period of time. Is this that some of them are going faster, some of them are going slower, some of them make more turns or less or something like that? So these are the questions. We answered to these questions. And by doing this, we managed to describe all caustics which generate periodic trajectories within ellipsoid in any dimension D, and to classify polydendric. So what I want to say is, so maybe I should stop here. Maybe this is a good moment to stop. That will be like a sort of introduction. So the further is to understand clearly, to understand this relationship, and so first combinatorial relationship between these A's and alphas, how they can occupy these endpoints of these intervals, and how to investigate this correlation between dynamics between these different lambdas in d-dimensional space, and then how to apply this to classify all periodic trajectory, all caustics we generate periodic trajectories in d-dimensional space for any d.
So Vladimir, as I understood, this movement along the trajectory is not related with the integrable systems of the kind geodesics on the ellipsoids. It is not. It is a different matter.
I would say it's very similar. I would say it's very similar. It's very similar in a sense. What we have here is this this is probably first of all, this is, I think, Charles' theorem that given a line and given confocal family of quadrics in d-dimensional space, there are d-1 quadrics from confocal family which are tangent to this line. But this can be seen as a manifestation of the fact that this the simplest problem of straight motion under inertia in d-dimensional space is integrable. You can see this that way.
Mm-hmm.
So I think that yeah.
Question. You know, your alphas and a's, they parameterize a hyperelliptic curve, right?
Yes.
So if not, and the curve may become singular, is it how it affects your picture when the genus is not right?
Yes, yes. This is excellent question. In this, you can consider this. You are getting then additional symmetries and these things. I put here this as this assumption that these A's are distinct. Distinct. I want to treat here only this generic case. But you are right, in a sense, when we can drop the genus by getting some of them coincide, and what may happen is, but then we're getting additional symmetry because of this rotational symmetry of this element. Let me show you one picture answering to your one of your questions. I have here, I prepared more than I showed. I can show this next time. But I have one picture which let me show it now. This picture is obtained in three-dimensional case when you have a 4-periodic trajectory, and then in a three-dimensional case you have 2 caustics. And they can be hyperboloids of the same type, and then in the situation where when they coincide, you're getting this picture, where this is this one double caustic. So these 2 hyperboloids coincided, and then billiard trajectory is placed that segments belong to these generators of this hyperboloid. And this is how you get this picture.
And another thing, your curve, you know, your hyperelliptic curve has a branch point at infinity, but you can consider the curve which, you know, has even number of points and a finite points.
This is correct, and actually in this second part of the future talk, we actually do this. We pass from one picture to another to achieve something. This is correct.
And I was thinking about these alphas and a's. It looks like alphas can you associate it with a level of some integral of motions of some Hamiltonians? Alphas, yes. And a's is not.
Yes, you're right. You're right.
Vladimir, in multidimensional case, the periodic trajectories, the question of periodic trajectories, could it be interpreted as a discrete integrable system?
A billiard system can be interpreted as discrete integrable system itself. So in a sense, yes, and we are getting nice combinatorial invariants. Pure combinatorial invariants. So in a sense, it's very, very discrete.
Okay.
It's even more discrete than we would maybe expect.
Okay. So if there is no other questions, I'd like to tell that we are planning to continue talks of Vladimir about this family of interesting questions, but we have to learn something before. So we are planning to organize some mini course for students in Yaroslavl State University. We have to decide about what part of this great story. Thank you very much, Vladimir.
Thank you. Thanks a lot. Thank you for nice questions and your attention.
Thank you all. Bye.
Thank you.